Good morning, my YouTube viewers. It's Crystal here. I haven't made a video in a couple of days because I've been really busy and studying. And basically, what I did was I've been studying neural networks. And there's not any neural networks in JAX. And since JAX is very similar to numpy, I decided to try to get some neural networks from numpy. And I did a blog post yesterday because out of exasperation, because I had been looking for neural networks. And basically, most of the neural networks that you get online where they give you training on it or education on it, they only train the neural network on a vector. Well, I didn't want to train the neural network on a vector. I wanted to train it on a data set. And so I went online and looked on all of these articles online to try to find a neural network that would work. But most of those neural networks train on vectors as well. And then I tried ChatGPT. I couldn't get a neural network to work either. Most of those were on vectors. And I didn't want it to train on a vector. I wanted it to train on a matrix, which is a data set. Or a data set, which is a matrix. And so basically, finally, I did this code review no, I didn't do a code review. I did a blog post on Medium, and I asked the question, why does Saturn Cloud put AI code on their blog? I mean, Saturn Cloud is a business, and Saturn Cloud wants people to use their Saturn Cloud services. And okay, I don't have any objection to using code generated by AI because I go on to ChatGPT and try to find code that will work. But Saturn Cloud doesn't even check the code to see if it works, which is ridiculous. And that was the point of my blog post, because I put the blog post out of exasperation. And I don't know, I just said, why do they put experimental code on their blog post? Because they're a business, and surely they can check the code before they put it on their website. Because one of the things that they did was they had an NP, that's numpy sigmoid. Well, numpy has no sigmoid function. So that obviously was bad code, and they put that on their blog post. So then I thought about it. I thought, well, what can I do? I'm going through searching for code, and I can't find any code. So I asked ChatGPT the question, would it make me a neural network in NumPy using the iris dataset? So I thought, well, that's a good idea. And it actually gave me some code. So what I'm doing is a code review on the code that ChatGPT gave me, and it actually works. So the first thing we have to do is we have to import the libraries that we're going to use. We're going to import NumPy as NP. That's your numerical computations. We're going to, from sklearn, import datasets. So we're going to import iris from that. From sklearn.preprocessing, import standard scalar. So we're going to scale the data using standard scalar. From sklearn.model-selection, import train test split. So we're going to split the data set up into training and testing sets. So those are the libraries that we're using. So the first thing we're going to do is we're going to load the iris dataset. Iris equals datasets.load iris. X equals iris.data. Y equals iris.target. And then what we're going to do is we're going to scale the data. So scalar equals standard scalar, x equals scalar.fit transform x. And then what we're going to do is we're going to one-hot encode the labels. Now the thing about the IRIS dataset, I think their labels are 0, 1, and 2. So num classes equals len, np, unique, y. There are 3 classes in the IRIS dataset, and I believe it's 0, 1, and 2. Y1 hot equals np zeros, y shape 0, so that's the number of rows and the number of classes. So I think it's got 150 rows times 3 classes. Okay, y1 hot, np arrange, y shape 0, y equals 1. So basically what's that saying is it's going to put the 1 in where there's a 1. So it's going to be 0, 1, 2. So if it's a 0, then you're going to get a 1 in the 0 placement. If it's a 1, you're going to get a 1 in the 1 placement. And if it's a 2, you're going to get a 1 in the 2 placement. And I wanted to do this particular blog post, and the reason why is because it's done differently. If you have, I know because I've worked with the IRIS dataset so many times, I know that their labels are 0, 1, and 2. But if you're working with a different label, then it's going to be different as well. And my next code review, I will explain that to you. And then what we're going to do is we're going to split the data into training and testing sets. X train, X test, Y train, Y test equals train test split. X, Y1 hot, test size equals 0.2, random state equals 42. Now what we're going to do is we're going to define the sigmoid activation function and its derivative. So the sigmoid activation function is 1 over 1 plus np exponent negative x. And then the sigmoid derivative is x times 1 minus x. Now we're going to define the neural network architecture. So input neurons is X train shape 1. So that is, I think it's 4 columns if I remember correctly, because you've got the sepal length and width and the petal length and width. So I think it's 4 columns. And they say input neurons, hidden neurons is 8. So they just take 4 and multiply it by 2 to give you 8. And output neurons is your num classes, which is 3. And so the hidden neurons are going to be 5 plus 3, because the hidden neurons are supposed to also incorporate the num classes into it. Now we're going to initialize the weights and the biases. So we have to set our seed, which is np.random seed 42, according to the Hitchhiker's Guide to the Universe. 42 is the answer to everything. So since 42 is the answer to everything, I put 42 on all my seeds. Weights input hidden equals np.random uniform. Size equals input neurons, hidden neurons. Biases hidden equals np zeros, 1 hidden neurons. Weight hidden output equals np.random.uniform. Size equals hidden neurons, output neurons. And biases output equals np0, 1, and then output neurons. So now we set up our hyperparameters. Hyperparameters is learning rate x1 and epochs is 10,000. And an epoch is every time you iterate it through it so many times. So we're going to have 150, well, we'll say, well, total with the data set it's 150. So 150 times 10,000 is going to be 1,500,000, I believe. Just thinking on my head. But we're not using all 150. We're using like maybe like 120. So 1,200,000. So we're going to say training the neural network. Let's see what we've got for, yeah, test sizes too. So we're going to say training the neural network. So we're going to set up a for loop for each epoch, and it's got 10,000 epochs. We're going to set up forward propagation. So let's look over here and say okay, forward propagation is where input data is fed through a network in a forward direction to generate an output. The data is accepted by hidden layers and processed as per activation function and moves to the successive layer. So that's what forward propagation is. So hidden inputs equals np dot dot, that's your dot product. X train, weights hidden, weights input hidden, plus biases hidden. Hidden outputs equals sigmoid, hidden inputs. So you're using your sigmoid. Final inputs equals np dot dot, hidden outputs, comma, weights hidden output, plus bias output. Final outputs equals sigmoid final inputs. And then we're going to calculate the error. Error equals Y train minus final outputs. And now we're going to check up back propagation. So let's just say, what is back propagation? Back propagation or backward propagation of errors is an algorithm that is designed to test for errors working back from output nodes to input nodes. It is an important mathematical tool for improving the accuracy of predictions in data mining and machine learning. So it tests for errors working back from the output nodes to input nodes. So output error term equals error times sigmoid derivative of final outputs. Hidden error equals output error term dot dot, that's your dot product, weights hidden output, and T is transform, so it transforms the matrix. Hidden error term equals hidden error times sigmoid derivative hidden outputs. And now we're going to update our weights and biases. Weights hidden outputs equals weights hidden output plus hidden outputs transformed dot dot output error term times learning rate. Bias output equals bias output plus NP sum output error term, axis equals 0, keep dims equals true times learning rate. Weights input hidden equals weights input hidden plus x train dot t dot dot hidden error term times learning rate. Biases hidden equals biases hidden plus np dot sum hidden error term axis equals 0, keep dims equals true, learning rate. So now we're going to test the neural network. Hidden layer input equals np dot dot x test, weights input hidden plus biases hidden. Hidden layer output equals sigmoid. hidden layer input, output equals input dot dot, hidden layer output, weights hidden output plus biases output, predicted output equals sigmoid output. And now we convert the one-hot encoded predictions to class labels. Predicted labels equals np.argmax. So argmax selects the largest number. Predicted output axis equals 1. And so axis equals 1 is a column. Calculate accuracy. Accuracy equals np.mean. Predicted labels equals ytest.argmax axis equals 1. And accuracy is 100%. So that particular neural network gave you 100% accuracy. And it worked. I tested it worked. So I do a lot better job than Saturn Cloud does. I don't think that Saturn Cloud should be putting defective code on their website because it's not doing their street credibility any good. I think that there's nothing wrong with them using experimental code. There's nothing wrong with them using AI generated code, but they should at least test it to make sure that it works, because on at least 2 occasions now I've gone on to Saturn Cloud and the code didn't work. And so, you know, how hard is it? I mean, they're just slapping these blog posts together, and how hard is it to check it to see if it works, because they're not doing anything but just upsetting people by putting code that doesn't work on their website. So that's it for this particular code review. This code review works. I tested it, and it works when I tested it, and so that's good going. A good thing to do is to test it, and we got 100% accuracy on the iris dataset. So I'm going to go ahead and close this video because I've been talking over 17 minutes. I would like to thank my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you want to be notified whenever I make a new video, please tap onto the bell button next to the subscribe button. And thank you for watching my video as I did a code review on a ChatGPT neural network.